Thank you, Prashant, for the kind introduction. Yes, it's good to see a lot of familiar faces today, but it's also good to see a lot of new people joining what I would say the DC movement, right, which is happening. Today, I am going to present the latest feature we added to DCIDE. DCIDE is basically DC Integrated Design Environment. It's a software platform we built actually to help you design and engineer DC microgrid concepts very quickly, very easily. And as you'll notice in past webinars, we have also shown that it has features like power flow analysis, where you can play with droop control, where you can run efficiency simulations, for instance. It has a lot of powerful capabilities to help you design and engineer DC microgrids. It has a DC microgrid product catalog as well in the background. So everybody who has DC products to share is more than welcome to join and list their products over there. You can get more information on our website. Visit dcide.app and you'll get more info. But today I want to share with you the latest we developed. And I think it's one of the biggest features we are about to launch, and that's DC wire sizing in there. So as a quick intro, here's like these sides. So you have an overall canvas essentially, which contains your single line diagram. Here I have a reference design of a DC data center that was recently published. You have components you can add on the side. You can drag and drop them onto your single line. And here we have like a DC architecture, which is AC grid connected, which can have a generator, which can have a battery storage system, 35 kilovolts AC. Then you step down to 800 volt DC, and you have server racks in here with battery storage in there. You can very quickly create these type of single lines. So here I'm connecting battery storage to a DC bus. I'm now connecting it to a load, which is supposed to represent a server rack in there. And you can rename it, label it the way you want. These changes get immediately reflected on your diagram. You can collaborate with multiple people together. This is online, so no offline installation required. Even during this call, you're more than happy to go there and try it out. We have a free version for that purpose. And that way you can really design at the speed of thought. Invite your coworkers as well to collaborate on diagrams in real time, leave comments, and basically have this design be your single source of truth in there. So as you see, as I'm setting up this demo, you'll notice actually in the sidebar that you can also specify voltages, currents, AC, DC, while you are designing. You have all the information in a single place. And if I quickly go over here, what you'll also notice here in the lower right corner is you get component suggestions. As soon as you start entering specs, you get recommendations on which equipment you can use. So DC microgrid equipment will naturally pop up there. We as a company have always been engineers. We have faced the troubles of finding the right microgrid equipment at the right time. It was always very complicated. So we started actually with DC product catalog that's behind this design. So that's a very quick overview. I recommend everybody to just experience it yourself and try it out. There are several reference designs that you can use as a starting point, or you can just start from a blank sheet quickly. Now let's get into wire sizing. So let's say we want to size this battery wire size. It's a 500 kilowatt hour battery. We have an 800 volt DC setting in there, and we want to actually derive for each wire the design voltage, the design current, to ultimately also then derive the wire size in there. In the sidebar, you'll notice that you can set all the installation conditions, grouping conditions of this wire. Like this is, for instance, installed on a cable tray or underground. You can all set it in here. But it all starts with figuring out how much current and how much voltage should this wire be able to carry. So that's where we got started. Like, how can I derive the design voltage and the design current? And actually, you always will derive this from the context of your diagram. So what I'm going to do now is I will actually enter how much kilowatt this server is going to draw from the system. So in this case, I'm going to set it up to be like 12 server racks of about 100 kilowatt each in there. And then if I navigate back to the connection, so we have 1.2 megawatts in total in there. Let's say our battery needs to be able to back up this entirely. You'll notice that now it starts in the background automatically for you, calculating what the suggested design voltage and design current can be. It takes into account bidirectional energy flows. It takes into account loads. So in this case, it recommends 800 volts, 1.5 kiloamps in order to be able to supply the loads. It derives that from the power and voltages you specify. In some cases, it is very straightforward, and you can just do that mentally by heart and very easily. In other cases with bidirectional power flow, it becomes very hard to juggle all the possible scenarios there might be. There might be current originating from solar. You might be charging your batteries. You might be actually supplying some EV chargers. This can get pretty mentally complicated to juggle for a human being. So we do a suggestion in the background automatically to evaluate what the worst case load of every connection can be. We do it for the battery connection, but you also see we do this for the connection that's originating from the grid. So in this case, if our battery needs to be able to back up the grid, it needs to be able to also supply 1.5 kiloamps from the grid side in there. All right, let's say we are happy with these values. Then you can actually readily adopt them. So you select the connection, you click to apply. If you want to have a different value, you can just enter it manually. If you want to apply it, just click it. Okay, 800 volts, 1,500 amps. And then if you scroll down, you'll notice we have suggested wire sizes. So here we have a place where we, first of all, calculate suggestible wire sizes. We calculate according to IEC standards what correction factors are in there. We calculate the maximum current per conductor and then the total current carrying capacity if you have, in this case, 6 times 300 square millimeter cable together. If you want to switch between IEC and NEC standards, you can readily do that. So you just go to the settings and you can adjust that directly from your design. Then you also get wire gauges instead of square millimeters, which our US friends like more, I guess. So here are all types of suggestions. The top 3 is the ones we'll recommend, starting with 6 times 300 square millimeters. We also show then immediately, based upon a 5% voltage drop, what's the length that you theoretically can cover with this in there. And you'll notice, actually, we ask very little information from the start in here. We just ask power, voltage, and you immediately get a sense of what size of wire you require. Next, you can go deeper and you can actually specify the installation conditions of this wire, the grouping, so how many wires are actually running in parallel or in close vicinity to each other. These all affect the wire size, adhering to the IEC standards in here. Then if you're happy with this wire size, you can actually apply the suggestion. So here I will change the installation method first. So I think I'm going to change it here to cable ladder, which is about 34, if I'm not mistaken. Yes. Okay, it sets up your defaults for you. And then you'll notice actually that this correction factor will be adjusted accordingly. In the grouping segment, you can then define how many of them are bunched together, whether they're in close vicinity to each other. And then here you always down below get your overview of the calculations. And you'll notice in this case that the maximum length has been reduced. If you apply the wire size, you'll notice that you have like a traffic light type of indicator because there's three things that we're checking for. The first check is, can this cable that I selected actually handle the rated current of my connection? That's the first green light. The second green light, which I'll show next, is the voltage drop in there. So if you hover this, you'll see, okay, we're in the rated current carrying capacity. Secondly, we haven't specified the length yet, so we cannot verify the voltage drop, so that's why it's yellow. And then the third yellow indicator is actually the overload protection, which I'll show next. So if you specify 600 meters, for instance, which is below the maximum length, you also get a green light here. If you specify longer than 697 meters, let's say 800 meters, you will immediately get a red light indicating you got to fix something. You have to upgrade your wire size. And then the third indicator is overload protection. So I'm zooming out quickly because I actually want to add overload protection to this connection. So I'm creating some space, moving down the battery, add a circuit breaker in between. This can be a mechanical one, this can be solid state. I mean, whatever circuit breaker we want to add, we're focused now on overload protection. Set the power flow direction appropriately, and this circuit breaker currently has no nominal current specified. So you'll see that actually immediately in the status message. So then you can go towards this Q1 protective device. You can set a nominal current. And then as soon as you've set your nominal current, you can go back to the connection. You'll notice that we in the background automatically derive that this circuit breaker is protecting this connection. And then we will check for, regarding the protection device, for three criteria. First of all, whether the nominal current of our breaker exceeds the design current of our connection. So it's exactly the design current, so we meet that criterion. Then we check whether actually our nominal current of the breaker is less than the current carrying capacity of the wire. Does it actually protect the wire? And then the last piece to check for in terms of overload protection is, does it actually trip before we start overloading the wire? So for circuit breakers, we have a 1.3 multiplier there according to IEC standards, and then a 1.45 times the current carrying capacity of the wire. This is another condition that you need to meet in order to protect this from overload. And then if you actually go through all your connections, we have one single place where you can generate a report. And this report actually shows you all the checks in here, whether they're satisfied or not, and shows you also a summary of all the parameters that have been added. This is a printable format you can use for adding it to your installation documentation and get your installation approved. All right, then let's run a second example. And after that, I'll stop for question. So I will now create an example for an EV charging station in there. I'm gonna add like 4 EV chargers of 150 kilowatts each. So I'm gonna enter that right away. Okay, here's charger number 1. I'm gonna copy paste 4 chargers, connect them to our main DC bus. You notice that our DC lines get marked right away, that the 150 kilowatt gets propagated. We're going to make them unidirectional, not V2G at this point. You can do V2G if you like. All right, set these all as loads like this. Then we will add some batteries for peak shaving purposes in here with a DC-DC converter. Let's set a nominal battery voltage of 800 volts for this example. I'm not gonna set any specs on this power converter, only the DC bus voltage. We're going with a default current OS 700 volt system in here. Then we'll connect to the grid. So AC in red, DC in blue. Specify a 690 volt three-phase AC system. Our AC-DC converter, let's make it isolated. And also do 700 volt on the DC bus side. All right. Now we're again going through wire sizing. So first question is, how much current does each cable need to handle? So we're going to navigate to the connections. And every 2 minutes in the background, this design current will get evaluated. If you want to trigger it manually, you can do that by the refresh icon. It starts calculating in the background. You need to give this some time. And after a couple seconds, you will notice that this connection will get specified in terms of the design current in here. So right, let's check whether we already have a result in here. All right, so here we have a result. So what has happened again in the background is we set up all the possible scenarios of how current might flow in this entire system. Your battery might be charging, discharging, you might be drawing power from the grid or sending power back to the grid from the battery, because we flagged it as bidirectional, and the 4 chargers will always draw current. So in this case, to meet the 150 kW requirement, it needs to be able to carry 214.3 amps. And then on the battery side, so you see these are all 214. Then on the grid side, if we want to meet the load, it's going to be like 4 times that amount. Let me quickly check. I think it's the next video that I got to play here for you. Yes, so on the grid side, you'll see we have 4 times that amount of current. Now, let's say if we want to limit our grid connection to 400 amps or equivalently, we set power on there or make it unidirectional. You see we can set that, and then again in the background, this constraint will get applied and your wire size will get recalculated automatically. Again, you can trigger it manually or it will happen after some time. So now it's recalculating 857 amps, 400 amps, because we set that this is limited to 400 amps. On the battery side, we still have the initial 857 amps current. We got to be able to run in here. Okay, and as soon as we have our specs for our connection, we apply them and we get again to wire sizing. So we get the suggested wire size in here, 10 options here, 3 recommended ones. Let's select the 150 square millimeter cable in this case. As soon as it has been selected, it again gets evaluated for current carrying capability, voltage drop, and overcurrent protection. You can do the same with the battery connection in this case. Okay, apply it. Then suggested wire sizes. You can apply the suggestion. And you repeat this process for every connection in your system. You can check the results in here. And for the other EV chargers, it's the same process that you run through. Then as a final example, I want to show if you switch to NEC, for instance, okay, NEC, Imperial, you'll see we get Fahrenheit, we also get wire gauges, and we get like 29 options for North American standard wire sizes in here. You can adjust the ambient temperature, for instance, to be the default 30 degree. And then you'll notice, again, similar to IEC, yet different correction factors, how the wire size can be in this case. I know this is a lot, and I have been very quickly explaining it. If you want to learn more, the past current OS webinars are definitely a place where you can go. You can also visit our website, DCIDE.app. We have a YouTube channel as well with past presentations and tutorials that you might visit. But I think the best way to learn and experience how it works is by trying it out. Go there, design a diagram, run a power flow simulation. That's something that I didn't cover in this presentation, but one in the past. You can, for instance, do efficiency analysis, specify the conversion efficiency of a power converter, and evaluate the losses overall. You can upload low profiles as well in here and check how voltages and currents propagate in the network. And if you want to try out wire sizing, it is available as of this week on our Pro plan. Pro plan is a paid plan in there, but because of this release and because of current OS, we have a special promotion campaign as well. You can get your coupon by sending us an email, sales@directenergypartners.com. Like the first 50 people that send us an email will get a coupon to try it out and join the initial wire sizing user base in here. All right, that being said, I'll